This is a really nice simulation about gas particles, and if we were able to zoom in and actually see what the particles look like, this is hopefully what we would see. We would start see a whole bunch of different atoms or molecules flying around, colliding with their container and colliding with each other. Now I'm going to stop it right here to let you focus. The um, the different colors on here represent different speeds. So I think the blue ones are the slowest ones, and I think the red ones or the red or the white ones are going to be the fastest ones. Sometimes when you have a whole lot of moles right there or a whole lot of molecules, you can get it quite busy, or whenever you have something close to a pure vacuum, you have something a lot like this. So I'm going to use this right now. Now, this is a perfect model of a gas, and we call this an ideal gas. That is the perfect gas that doesn't actually exist, but we have to base everything off of the perfect paper volume. So we call that the ideal gas, and we assume 5 things about an ideal gas. That comes from our kinetic theory. First thing we assume is we assume that the gas particles have no volume. The gas particles are so teeny tiny that they have absolutely no volume. So all of this stuff, all this black stuff in the middle, right here is all empty space, and that's where our volume comes in. The particles themselves have no volume. Now we assume that the gas particles are always in constant motion, so they're always moving around, bouncing into different things. We assume that when those gas particles collide, that there is no loss. Let's put a little more in there. There is no loss of kinetic energy. Now what this means is that the kinetic energy may transfer from one molecule to another, but it will not lose kinetic energy overall. This is different than what you would see by taking a baseball or, hitting a bat, or a tennis ball hitting the wall. It will transfer its kinetic energy, but will also lose some kinetic energy and turn it into potential energy. So, but that is not the case here. We assume that all these collisions are elastic or have no loss of kinetic energy. Now, for the fourth thing that we assume is that the particles do not attract to each other, or they do not repel from each other. There's no intermolecular forces. So whenever they come close to each other, they don't start to have influences. They can run into each other, but they don't attract. And then for the fifth one is that we assume that the average kinetic energy has to do, or the energy of the energy of motion has to do with the temperature, and it's directly related. So I'll demonstrate that by adding some heat right here. If I add the heater, which you can see it's this vibrating line down at the bottom, the particles start to move faster. So they start to gain more kinetic energy. And that's so we'll move ahead to page 2 in your notes and discuss we'll go ahead and fill in the blanks and discuss what kinetic theory and what an ideal gas is. I will be reading the notes. You may skip ahead and as you need to, but I'm just reading for those who need to hear the words. So the kinetic theory of gases provides a model of an ideal gas that helps us understand the behavior of gas molecules and the physical properties of gases. An ideal gas is an imaginary gas that conforms to all the assumptions of the kinetic theory. The kinetic theory is based upon the following 5 assumptions. And I discussed this in the simulation just before. Number 1, the gases are composed of large numbers of tiny spheres. The particles are so small that they occupy essentially zero volume of the gas itself, and there is a large amount of empty space between the particles. Therefore, a gas is mostly empty space. This is why gases have low density and are easily compressible. The particles of a gas are in constant motion and move rapidly in straight lines in all directions until a collision occurs. Now, the collisions between gas particles and between gas particles in the walls of the container are perfectly elastic. An elastic collision is one in which there is no loss of kinetic energy. This is the one that a lot of students have trouble with because they think of gas particles as tennis balls, and tennis balls do lose their kinetic energy, but gas particles do not lose kinetic energy when they collide with things. So now, number 4, there are no forces of attraction or repulsion between the particles of gases. And number 5, the average kinetic energy of the particles of a gas is directly proportional to the absolute temperature of the gas. Now, absolute temperature, that's going to be on the Kelvin scale. And there's a reason why we use Kelvin, because it is absolute. Celsius is based off of the temperature of water, and Fahrenheit is based off of something else. But Kelvin is based off of like an absolute, real life, universal sample of absolute zero. So, the ideal versus real gases. An ideal gas is an imaginary gas that conforms to all the assumptions of the kinetic theory. It only exists on paper. Okay, so ideal only exists on paper. Now, the gases you're breathing right now is a real gas. A real gas, such as nitrogen or oxygen, can conform to all the assumptions of kinetic theory. When this occurs, we say the gas is behaving ideally. However, a real gas will not behave ideally under all conditions of temperature and pressure. When a real gas is not behaving ideally, it implies that one or more of the assumptions of the kinetic theory is no longer true. Real gases will lose their ideal behavior when the pressure is high and the temperature is low. That is exactly like summer vacation, all right? So all my students behave most ideally when the temperature is high and the pressure is low. You're not in school, so you're at low pressure. You're able to sit on your couch, watch Netflix or whatever, and the temperature is high outside because it's summer. So the students also behave ideally whenever this happens. So that's a great memory trick for you to think about. Is think about summer vacation. Now, at high pressure, the particles get much closer together and the gas is no longer mostly empty space. Assumption number 1. At low temperatures, the kinetic energy is so low that there can now be attractive forces between the particles. Assumption number 4. So you guys are familiar with temperature and you're familiar with volume, but you're probably not really familiar with pressure. And so let's discuss exactly what it is. It is defined as the force exerted by a gas per unit area, okay, on a surface. So it's the force divided by the area. And we measure force in newtons. So you may see in physics newtons per meter square. That's a valid thing, but you won't know that till physics. Result in pressure results from the simultaneous collisions of billions and billions of gas particles with the walls of the vessel containing the gas. So if you recall that simulation I showed, it's the particles actually colliding with the container, not themselves, it's with the container. So now atmospheric pressure results from the collisions of air particles with bodies exposed to air. And the pressure is measured with an instrument called a barometer. Barometer. You've heard your weatherman call it barometric pressure. That's what he's talking about. A column of mercury will rise to an average height of 760 millimeters in a barometer at sea level. This is our basis for measuring pressure. So we actually have a unit called millimeters of mercury, okay? And that's listed right here. 760 millimeters of mercury is atmospheric pressure. Now we also use the value of torr because Torricelli was the first person who came up with this. So we named the unit after him. We just shortened it. And but this is actually what you're feeling right now because we live at 1 atmosphere or close to it. Now kilopascals is based off of the SI unit, and that's based off of newtons per meter squared. And sometimes you run into that. Okay, so those numbers are there for you, and you don't have to memorize them. They're just already there. So the conditions of 1 atmosphere pressure and 0 degrees Celsius are known as standard temperature or pressure, or STP. You must memorize what STP is, okay? STP is at 1 atmosphere and 0 degrees Celsius, or 273 Kelvin, okay? Or 0 degrees Celsius. These are important conditions because it allows scientists to just kind of set a baseline. So let's do example number 1. A gas exerts a pressure of 1.3 atmospheres with the equivalent pressure in millimeters of mercury. So this is just a unit conversion, 1.35 atmospheres. I just need to convert atmospheres to millimeters of mercury. It's just the easy two-step process. And we know from our equation above that 760 millimeters of mercury is 1 atmosphere. So just multiply the two of them, and we end up with 1,030 millimeters of mercury. And then a vacuum pump evacuates a container until the pressure reaches 250 millimeters of mercury. What's the pressure in atmospheres? So it's just backwards. Millimeters of mercury. So, and then take millimeters of mercury and atmospheres. There are 760 here. Millimeters of mercury in 1 atmosphere. So 205 divided by 760 will land you at 0.270 atmospheres. So that's what we run into, and really for these two examples, you're either multiplying or you're dividing 760, and that's really all you have to do. Okay, all right, thank you all.